Okay, so let's look at the ratio test. The ratio test is the most important test. So I'm going to put a star next to this guy. Out of all the tests, this is the test you're going to use the most, and we're going to revisit it once we start looking at intervals of convergence, radius of convergence. All of those are going to do the ratio test over and over again. So right now, this is kind of the intro of the ratio test. So you have some series. A to the n represents kind of that function, right? A to the n is like 1 over n squared, e to the n over n, whatever. This is the series, and you're looking to see whether that has an infinite sum or a finite sum. And so the ratio test says this. We can look at the limit of a to the n plus 1 over a to the n, and we can get some limit. If that limit is less than 1, it converges. If the limit is equal to 1, it's inconclusive, meaning we're not really sure what the result is. In reality, you shouldn't have done the ratio test anyways. And if it's greater than 1, then we know it diverges. It's kind of hard to explain this without just doing some examples, so let's just go through some. So let's look at this particular series. N squared over e to the n. And goes from 0 to infinity. Okay, so in this particular case, n squared e to the n, that's our a to the n. And we're really not sure. Now, let's take a step back and say, okay, don't we really know? We have to know. E to the n is an exponential. This exponential is going to dominate this polynomial. The ratio test is just proving that this does in fact converge. You have to be able to look at this and know that it converges. E to the n is going to grow so fast to infinity relative to n squared that this thing's going to go to 0 so stinking fast that of course it has a finite infinite sum. Okay? So we have to be able to get that general idea of what's going on here, but the ratio test is going to prove that for us. So we look at the limit of a to the n plus 1, which is just shifting all of these, n plus 1 squared, e to the n plus 1 over a to the n. Well, that's just the original function, n squared over e to the n as n goes to infinity. Okay, so when n goes to infinity, and again, this is where L'Hopital comes back into play. So L'Hopital is going to allow us to do all this sort of stuff. So L'Hopital says n plus 1 squared over n squared. Well, as n goes to infinity, that limit is just 1. So they're the same. Polynomial growth, n plus 1 squared and n squared are the same. Now this is e to the n plus 1 over e to the n. So if I simplified this e to the n comes to the numerator. And e to the n plus 1 is really e times e to the n. That's the whole plus 1. It's one extra factor of e. Well, e to the n and e to the n cancel, and you're left with 1 over e. And you're like, huh, look, I found the limit of a to the n plus 1 over a to the n as n goes to infinity, and I got 1 over e, which is 1 over e is less than 1, so this series converges. Yay! Right, and we knew this converged. Okay, we knew that this this exponential dominated this polynomial. We can prove that, to be true. We can look at any of those kind of polynomials. And again, when you do the ratio test, you can see that when you add 1 to the polynomial, not much is going to happen. When you add 1 to the exponential, then you can show that it grows. So we can look at about n equals to 1 to infinity over, 2 to the n over 5 square root of n. Now again, in this particular case, see how the exponential is on top and the polynomial is on the bottom? So this is going to grow, and so this thing's for sure going to diverge, but I can use the ratio test to prove that. So we need to look at the limit as n goes to infinity of 2 to the n plus 1 over 5 times the square root of n plus 1 all over 2 to the n over 5 times the square root of n. Okay, the 5's cancel, right? The 5 had no effect on anything. Excuse me. The limit as n goes to infinity, the square root of n plus 1 and the square root of n are the same. And then this is one extra factor of 2. So you get the limit of 2. 2 is greater than 1, which says this diverges. And we knew it diverges. The polynomial dominated. Here, we knew that converges. We're not actually finding what it converges to, but we do know it has a finite sum, and we're saying what this has is an infinite sum. And again, the ratio test is the best at talking about polynomials with exponentials, or polynomials and exponentials, and maybe even factorials. So what if I had something like this? What's the sum of 5 to the n over n factorial? And we'll go from 0 to infinity. In this case, we need to prove that the factorial dominates the exponential, and the ratio test can show that for us. So we look at the limit as n goes to infinity of 5 to the n plus 1 over n plus 1 factorial all over 5 to the n and n factorial. Okay, so let's think about this. We know what happens. The 5 to the n plus 1 and 5 to the n, we know that's going to be one extra factor of 5. And so this is going to cancel and give us a 5. And I won't skip any steps this time. Let's go ahead and multiply by this reciprocal. So this is 5 times 5 to the n over n plus 1 factorial. Right, dividing by this is the same thing as multiplying by this. We know that this and this, right, those are going to cancel and leave us with a 5. And then the question is, what in the world is n factorial over n plus 1 factorial? Well, okay, so think about this. What's 8 factorial over 9 factorial? That's really the situation we have here, right? See how the denominator is n plus 1 factorial? It's one bigger factorial than the numerator. But that's 8 factorial. And what is 9 factorial? Well, the definition of 9 factorial is 9 times 8 times 7 times 6. But 9 factorial is really just 9 times 8 factorial. Because 8 factorial is 8 times 7 times 6 times 5. And then 9 times that is really the same thing as 9 factorial. Well, that cancels. And so when you do 8 factorial over 9 factorial, the denominator just has one extra factor of 9. So that would just be 1/9. So if you're looking at n factorial over n plus 1 factorial, you can rip off that lead term of n plus 1, because n plus 1 factorial is n plus 1 times n factorial. And then those cancel. And so what you're left with here is you're left with this 5, and you're left with that factor. 5 over, this is n plus 1 bigger than n factorial, and we're left with that. But we have to look at the limit as n goes to infinity. As n goes to infinity, this is in fact 0, and since the limit is less than 1, we know this converges. And again, this is me proving the fact that this factorial dominates exponentials. Again, you're going to use the ratio test when you have combinations of polynomials or square roots and logarithms with exponentials and factorials. And again, don't just use it when you have polynomials. So if you had something like the square root of n plus 4 over, n squared, do not use the ratio test here. It's not going to prove anything. Right? This is really a p-series test or an integral test, not the ratio test. If you did the ratio test on this one, which you're never going to do, you're going to get an inconclusive result. Because if you looked at this, you're going to get a to the n, so add 1 to that, makes that 5, over n plus 1 squared, all over the square root of n plus 4, all over n squared. But we know that when n goes to infinity, the square root of n plus 5 and n plus 4 is just 1, and n plus 1 squared and n squared is just 1. So that whole thing is just 1, which is an inconclusive result of the ratio test. We do not use the ratio test when we have stuff like this. We would really say this is pretty much n to the half power over n squared, which is in fact 1 over n to the 3 halves, and then a p-series test would say that this is converges, but not the ratio test. The ratio test is for factorials, it's for exponentials, and with combinations of those other things. So let's just do one kind of final example here. Let's do one where it's got everything in it. Okay, so let's say it's the weirdest one like of all time here. And it is, we'll go from 1 to infinity, of 3 to the n times the natural log of n over the square root of n times 2n factorial. Okay, now first, what happens here? Not really a big player, not big player, exponential, factorial. Factorial is going to win. So we know this thing converges, and let's just use the ratio test to prove that. So we want to look at the limit of 3 to the n plus 1, the natural log of n plus 1, all over the square root of n plus 1 times, ooh, now this one's hard, 2 times n plus 1 factorial. Gotta be really careful with that one. You have to add 1 to the n. Adding 1 to the n is going to make this 2n plus 2 eventually, right? Adding 1 to 2n actually adds 2 to something. You got to think that through. Then 3 to the n, natural log of n, square root of n, 2n factorial, and again we're looking at the limit of that as n goes to infinity. All right, so what happens here? Well, as n goes to infinity, the square root of n plus 1 and the square root of n, those are just 1, right? Because as n goes to infinity, those are the same. The natural log of infinity plus 1 and the natural log of infinity, those are the same, so they cancel. This guy and this guy can just create a 3. So we know there's a 3, and where is it? Well, it's in the numerator. And then the question is, what is this versus this? Okay, this is in the denominator's denominator, so it's going to pop up in the front. So this is 2n factorial. This is 2n plus 2, distributing that 2 factorial, and that's 2n factorial over, and again, this has 2 extra terms, right? 2n plus 2 is 2 bigger than 2n, so this is 2n plus 2 times 2n plus 1 times 2n factorial. This is like 8 factorial over 10 factorial. 10 is 2 bigger than 8. And so this and this cancel, and you're left with both of these guys. And hopefully you can see that as I let n go to infinity, this of course is 0. And since it's less than 1, we know that it converges, and we already knew it converges because we know that this factorial dominates. Okay, so that is the ratio test. The ratio test is going to solve questions when you have a series of some a to the n, and a to the n involves exponentials, factorials, with or without polynomials, and logarithms. Just don't use it if it just has polynomials. Okay, and again, you're looking at this limit, and you want to show that the limit is less than 1, then it converges. If it's equal to 1, well, you probably shouldn't have done the ratio test. Or if it's greater than 1, then you know it diverges. Okay, most of the time you're going to do the ratio test and you're going to know whether it converges or diverges, because if it was just polynomials, like the example I showed, then you probably were going to do the integral test or the p-series test or some comparison test.